For decades, the standard heuristic for how the brain handles information has been a straightforward, linear assembly line. An event happens, it enters short-term memory, sits briefly in an intermediate memory phase, and is finally filed away into long-term memory. This model relies on a specific structural assumption. It treats the intermediate phase as a passive holding container, waiting for the brain to simply strengthen an already complete, intact representation of the original event. The Brain Kinematics Model, or BKM, strikes through this logic. Looking at this diagram, we have to abandon the idea of memory as a set of static boxes. BKM proposes that memory consolidation is an active, progressive, multi-scale organizational transformation. It does not happen instantly upon encoding. It develops across multiple waking and sleep cycles. This model suggests that by day 10, the internal physical and relational structure of a memory has undergone a total reorganization compared to its state on day 2. Memory is never truly placed in a storage container. It is a substrate that is continuously rebuilt, differentiated, and restructured. This photograph captures the active biological work required for that structural transformation. Sleep provides the specific neurophysiological environment where memory reorganization accelerates. The complete BKM equation tracks several specific variables to measure this reorganization: component differentiation, strain stabilization, the formation of shared units, thematic integration, and affective reorganization. These variables do not operate in a sequential sequence where one finishes before the next begins. They are parallel, mutually modifying processes. A shift in the emotional weighting of a memory happens concurrently with its physical structural differentiation. To accurately map how a raw sensory experience becomes a consolidated memory, we have to track two opposing trajectories simultaneously: differentiation moving downward and integration moving upward. The first stage of the BKM architecture begins with waking encoding. A specific external event occurs, initiating distributed sensory and perceptual activity in the brain. In this diagram, we see the BKM waking equation in motion. An initial input triggers a raw, developing trajectory of neural activity, but that activity does not develop in a vacuum. During waking hours, it is immediately hit by complementary boundary inputs, continuous streams of sensory, interoceptive, and environmental constraints. If you expect a coffee cup to be on your desk, but your hand hits empty space, new sensory information instantly redirects the developing cognitive organization. These external boundaries force internal neural activity to conform to external physical reality. Reality correspondence relies on this recurrent, feedback-dependent loop. Waking memory formation requires continuous external correction. Immediately following an event, its memory representation is what BKM terms a cloud, an overlapping, incompletely differentiated state. This left side of the diagram illustrates stage B of the architecture, downward differentiation. Over successive cycles, the initial memory cloud breaks down into large event-related pieces, then smaller feature bits, and finally into pixel-like components. BKM defines these pixels as fine-grained functional organizations operating at the scale of small neural groups. On the right side, we see stage C, upward integration. This happens at the exact same time as differentiation. Different memory networks contain overlapping components.
Through repeated activation, components that are shared across multiple different memories stabilize into what the model calls shared memory units. These shared units provide the actual biological architecture for overarching thematic memories to emerge. This creates a highly efficient system. By differentiating an event into highly specific, fine-grained components, the brain creates building blocks that can participate flexibly in massive, complex thematic networks. Greater structural differentiation does not cause a memory to become isolated. It is the exact prerequisite required for reconstructive thematic integration. When the brain transitions from waking reality into sleep, the constraints governing these trajectories change entirely. The external sensory boundaries that forced the neural network to match physical reality are severely reduced. Without that continuous external correction, the developing neural trajectory defaults to internal constraints. Its organization is now driven by memory, emotion, and overarching themes. This lack of external boundaries grants the system immense operational freedom. memory fragments and relational structures can combine and recombine without having to pass a waking correspondence test against the physical environment. This yields a defining maxim of the BKM architecture. Dreams may be poorly reality-bounded, but they are strongly theme-bounded. A dream featuring physically impossible locations or contradictory timelines is not a neural error. It is a highly successful organizational operation executing precisely under internal thematic logic. To observe this reconstructive logic, the source text details a specific case study, the package dream. A dreamer sees an old, unused professional package currently held by a colleague and feels zero anxiety about letting that colleague keep it. This diagram maps the dream's architecture. The bottom layer consists of episodic pieces, the specific workplace, the physical package, the colleague's face. But the middle layer executes a life history evaluation, calculating the counterfactual opportunity cost. The top conceptual layer resolves the emotional weight. It categorizes the package as a sunk investment, allowing the dreamer to release the historical cost and move on to current work. The thematic layer actively recruited specific shared memory units from the episodic layer to perform this higher-order calculation. Thematic memory is an active, reconstructive organization mechanism capable of actively resolving emotional weights. BKM proposes a highly specific temporal window for this transformation. Based on observational data, the model suggests this differentiation and integration process peaks roughly 7 to 10 days after the initial event. This timeline allows the model to generate falsifiable predictions regarding dream lag. BKM predicts that as consolidation progresses over those 7 to 10 days, the literal episodic resemblance to the original event in a person's dreams will systematically decrease, while the thematic and emotional continuity will persistently strengthen. These variables culminate in stage E, multi-scale relative strain stabilization. A consolidated memory reaches a dynamically bounded, stable range across local, regional, and cortical scales. Memory consolidation is an ongoing physical calibration. The neural system achieves exactly enough stability to maintain its identity, while remaining structurally flexible enough to learn.